So Nima will give the last talk of our KITP retreat on the there and back again at positive geometer scale. Please.
All right. It's really wonderful to be able to join you guys. As Lauren was saying, it's too bad that we can't be in the paradise of KITP there together. Earlier today, we went through a tornado warning, and I spent part of my day in the basement. So that's. But anyway, I'm delighted to be able to give this talk. So the title is obviously an allusion to the Lord of the Rings. Coming back to the KITP is like coming back to the Shire after 3 years of insane adventures out in the wilderness. So that's I want to tell you something about these adventures. That the past 3 years have been especially intense in the developments of this general subject that I'll be talking about. And in the first part of this talk, I'd like to just sort of quickly review some of the things that have happened and mostly talk about a number of new directions. So I'll just throw out in a minute or two a few different ideas that are sort of pushing on from these general themes. And then if there's time, towards the end, I'll take one example and talk about it in a little bit more detail. This is the story of cluster hedra that I talked about already at amplitudes, but there have been a number of new developments since then. And anyway, if we have time, we'll get to that. So I don't need to go through this philosophy again with this group of people who've heard me saying these words for the past decade or plus. We're interested in the question, what is the question to which the scattering amplitudes are the answer? And amplitudes only depend on on-shell kinematic variables. They depend on some kinematic space. But every usual approach to computing them invokes some auxiliary space beyond this kinematic space. Most obviously, Feynman diagrams invoke the interior of space-time in order to calculate this otherwise on-shell process. All these virtual particles, finite scale propagation in the interior of space-time. Which isn't there in the final answer, which only involves the on-shell things in kinematic space. Or in string theory, you do some auxiliary calculation on a two-dimensional world sheet to get the answer to scattering amplitude. And before 2017 and the KITP program, in the context of planarity equals 4 super-Yang mills, what we've been pursuing with a variety of friends was another way of thinking about scattering amplitudes. Somewhat more abstract, involving ideas in combinatorics, total positivity, and the Grassmannian that grew into the picture of the amplituhedron as Grassmannian generalizations of polytopes, together with the more general ideas of positive geometries. So compact regions in some general spaces with boundaries of all codimension, those being the positive geometries, and then certain canonical differential forms that go along with those geometries that are fully determined by those geometries by the requirement of having singularities, logarithmic singularities on and only on all the boundaries of those spaces. So now something important happened in 2017. In fact, it was first reported at the KITP meeting in 2017 that represented a turning point in this entire approach. The main idea is that we can see all of these things no longer in auxiliary spaces, but directly in kinematic space. So scattering amplitudes are differential forms, and we can see the positive geometry directly in kinematic space. And this was first seen, so just to give the first point that we can think of amplitudes as forms, well, we're very familiar with that already just at loop level. There's a one loop integrand, and we think of it as a form with the d4x in there, of course. And one interesting fact already is that when you think of this as a form, after looking at it for a while, you can recognize this as the wedge product of 4D logs. Such a simple one-loop massless box is actually the wedge product of 4D logs. And the fact that it's a wedge product of 4D logs reveals the beginning of the sort of revelation of the connection of these ideas with the positive geometry. So that we're familiar with when we're talking about loop integrands, but we can also talk about amplitudes directly as forms. The sort of most obvious idea, you can even apply this to the standard model, is we normally can't combine amplitudes of different velocities together in one object purely using on-shell ideas, but we can if we take a positive velocity gluon amplitude and we wedge with a d squared lambda, and similarly for the negative velocity gluons. So this lets us talk about scattering amplitude as a differential form on lambda tilde space, where the differential form is capturing the helicity information. You can also do this for superamplitudes. You can convert superamplitudes into differential form simply by taking the Grassmann eta variables and just replacing them with the dz. So in momentum twistor space, familiar R invariant like this, after you make this replacement, and only after you make this replacement, as above in the loop example, you actually recognize that this very familiar object is really secretly the wedge product of 4D logs. And that, again, is the beginning of of seeing that there's some positive geometry directly in kinematic space. And what Hugh Thomas talked about with our joint work with Yara back in 2017 is that we can think about the amplituhedron in kinematic space exactly like this. So the kinematic space is the n momentum twistors. At loop level, we're talking about the integrand, so we have L lines in momentum twistor space. And the idea was that there's a positive region in momentum twistor space specified by some topological or sign flip criteria. There's a family of hyperplanes of appropriate dimensionality, and we have a form that lives in this big kinematic space, which has the property, well, this hyperspace, these family of hyperspaces intersects this positive region in literally the amplituhedron. But now we see the amplituhedron directly in kinematic space, and the scattering form lives directly in kinematic space, and it's fully determined by the fact that when pulled back to the subspace, you get the canonical form for the corresponding amplituhedron. So I've written down here the entire definition of the amplituhedron at all loop orders. It fits on half a page like this. And what's sort of remarkable is that all these positivity and sign flip conditions have all the magic in them needed to give rise to factorization and forward limits and all the stuff that we expect should be there at the level of the full integrand. One of the developments more recently that we've just been talking about is the analog of this directly in momentum space for the momentum amplituhedron, where you think of the scattering of the superamplitude again as a differential form directly on lambda tilde space. Okay, so that idea that is now encouraging us to think about is a more general idea that we can use in many contexts. We'll come back to a number of other contexts in a second. The idea that we should be looking for these geometries directly in kinematic space. But let me begin by talking about some developments associated with planar n equals 4 superangles. Well, the first thing that we'd obviously like to do is not talk about the integrand, but directly talk about the amplitude. But taking some inspiration from the story of the amplituhedron, see if there's some kind of non-perturbative geometry for planar n equals 4 superangles amplitudes that would play the role for the full amplitude, perhaps even non-perturbatively, that the amplituhedron does for the integrand. And there's an obvious place to begin, which is to think about the region associated with the external kinematic data for the amplituhedron, even specializing to MHV. We're invited to think about the positive Grassmannian G4n for the external momentum twisted data, but we know that the final answer is only a function of cross ratios. You see, the interesting thing is that the overall scaling of the momentum twistors keeps track of helicity information, but after we strip off the helicity information, which there's nothing to do for MHV, we're only left with things that are functions of cross ratios. So that's the positive Grassmannian modulo torus. And so this is the sort of most obvious place you'd like to begin to think about what the non-perturbative geometry might be. But it's not obvious a priori what this is, so what you should precisely mean by the positive Grassmannian modulo the action of the torus. Now, I should say ahead of time, there's an encouragement for why we should be looking for non-perturbative geometries, period, which comes from work of Mark et al. That we know there are finitely many solutions to planar Landau equations. And so there is a hope that there's an autonomous geometry that captures all of these singularities, again, as an answer to a different question, just as the amplituhedron does for the level of the integrand. But now we have a more concrete question to try to figure out what the positive Rashomonian mod torus might mean. And a general point is that this notion of stringy canonical forms gives a natural definition. If we apply this notion, that's where the language came from to begin with, to the case of the positive part of G2n, then we go from the positive part of G2n to the certain set of integrals associated with the integration over the positive part of G2n that we just recognized modulo torus as being an integral of a string worldsheet. And this defines what we mean by the compactification of the corresponding space, whose boundary structure in this case is that of the icosahedron. But if we now mimic this for our larger problem, where we have the G4n instead of G2n, then this gives a richer and more interesting space. And in fact, this space is related to what we just heard in Lauren's talk. It's related to the tropical positive Rashomonian, the Dressian, and so on. But for our purposes, it defines a compactification of the corresponding cluster algebra for G4n with a finite number of letters for the symbols, an interpretation for the algebraic ones that are not cluster variables. So there's a few encouraging signs that this space is right, although we have to think a lot more about it. But still something that's missing is what is the question in this interesting space, G4n mod torus, to which the amplitude is the answer. Perhaps non-perturbative amplitude is the answer. We don't have a picture yet for what such a question might be. It's the analog to the amplituhedron. In other words, it's like we have the analog of the amplituhedron, perhaps. But for the amplituhedron, we know to ask what is the form with logarithmic singularities on the boundaries of the amplituhedron. We don't have the analog of that question here. I want to mention another more recent thing, which has come up actually since the amplitudes meeting. This is a work in progress with Johannes and Yara, which is just that even for the simplest problem of the n=4 amplituhedron, there's a new way of making a contact between geometry and amplitude. So if we look at the positivity conditions that are satisfied for the n=4 amplituhedron, we have L loops, so there's some trivial positivity condition for each loop separately, but the really interesting one is this mutual positivity condition. And this is the thing that's really novel at the multi-loop level. It's even a kind of a novel sort of positivity. Now, what we're supposed to do if we think about the amplitude or the integrand of the amplitude, then is to imagine we plot down L nodes representing each loop and demand that they're all mutually positive with respect to each other. Now, a very simple bit of combinatorics, essentially trivial bit of combinatorics, tells you that this guy is actually the same as the exponential of summing over all the connected graphs, where I draw any connected graph. This is a complete graph. Everyone is connected to everyone. Here I just sum over connected graphs. I'm allowing things not one doesn't have to talk to three, but now I impose negativity conditions for all of these guys. Okay, so this is interesting because it tells us the amplitude is naturally the exponential of something. And what is the exponential of? The log of the amplitude actually has a beautiful positive geometric meaning. It's just different regions of the amplituhedron with different sign patterns. However, each one of these regions doesn't actually correspond to any planar Feynman diagram. So that's kind of interesting. It's a different way of organizing the thinking even about the n=4 problem. And it allows us to naturally connect these positive geometries to finite polylogarithms that are a function of a single variable. So if you take any one of these regions, then it's very simple to show. If you just make one of the loops special, I'm calling it AB0, and you integrate over all the rest of them, the answer is actually finite. And it depends on a single variable, which is the cross ratio that you make between this last loop and the external points. So for instance, this is the answer you get from this graph. This is the answer that you get from this. So this is some weight 2 function. This is the answer you get from this graph. It's some interesting weight 4 function. And we can even sum infinite classes of these diagrams. This is the sort of analog of summing ladder diagrams, if you like, except they're not ladders. They're not really diagrams. They're natural positive regions, amplituhedral regions. But we can sum all of these guys and get interesting results at finite g. There should have been a g inside that cos pi. Okay, so this is I think it's a promising approach to try to directly go from some positive geometry to some unambiguous polylog, and to try to understand how it works. And in fact, there's a natural geometric strategy which is that all of these different positive geometries of these different sign patterns should provide a basis for the d-log part of the twisted cohomology in these spaces. And if that's the case, there would be a direct path from the geometry to the differential equations that Johannes in particular loves so much, that would directly determine the answer. All right, so that was the summary for what's going on in planarity equals 4 super-Yang mills. Now let me very quickly talk about some of the other developments. So first, there are developments in non-supersymmetric and totally non-planar theories. I'll say more about this at the end, so I'll go over this quickly. Here we have yet another way in which the amplitudes are formed. Now we're talking about a different theories, just simple scalar field theories in any number of dimensions. In fact, formally, D goes to infinity number of dimensions for the biadjoint phi cube theory, so we ignore all Graham determinant constraints. In this case, the natural kinematic space, or the space of Mandelstam invariants. And instead of talking about as an amplitude as a function, 1 over s plus 1 over t, we think about it as a differential form, d log s minus d log t. The minus sign is important, and it's non-trivial that it's possible to choose all these signs for general graphs so that the form has a projective invariance. This projective invariance is analogous to the dual conformal symmetry of n equals 4 super-Yang mills for this theory. And there are positive geometries that capture the amplitudes. At tree level, there are the ADHY isosahedra, which also give a very simple conceptual explanation of the CHY map as an example of stringy canonical forms, mapping one positive geometry to the other. In particular, mapping the world sheet directly into this into the ADHY isosahedron in kinematic space. More recently, there's a story extending all of this to one loop and finite type cluster polytopes associated with these objects are binary geometries that give us generalized string amplitudes and things that I'll talk about towards the end today. In these same theories, moving to all loop orders and all orders in the 1 over n expansion, so it's nothing to do with planarity, are these general notions of cluster hedra. I'll also mention that these ideas have been extended to general theories, phi to the 4, phi to the p, for trees, and even recently at one loop, where the words are Stokes polydopes, accordiahedra, etc., from some quite lovely series of papers from India. Okay, so now moving on, a third development along these lines is extending some of these ideas about scattering amplitudes to more general observables. And one of the sort of prime motivations, at least certainly one of my prime motivations for thinking about scattering amplitudes as a kind of a warm-up problem for thinking about harder cosmological questions. But in fact, we can go back to easier cosmological questions just in perturbation theory. And in cosmology, we calculate spatial correlators at late time, so we can think about these in momentum space as associated with polygons like that that close because of momentum conservation. And a very beautiful thing is that scattering amplitudes actually live inside cosmological correlators. So if you take these cosmological correlators and you take a certain analytic continuation of the momenta, so that the sum of the magnitude of the momenta goes to 0 to mimic energy conservation, then the correlators pick up a singular piece. And what multiplies the singularity is the on-shell scattering amplitude. And what happened since 2017 is that there's a beginning of an on-shell approach to inflationary correlators, as well as a beginning of an understanding of positive geometries associated with just single Feynman diagrams, even at the moment. But already here, the connection between the correlators and the amplitudes has been useful. So all of these polytopes have a particular face where all these energies add up to 0 that corresponds to the scattering amplitude. And thinking about the scattering amplitudes in this language gives, to my mind, the cleanest understanding of the cutting rules for scattering amplitudes. Some work to appear that Paolo Benincasa was just telling me about with some of his collaborators also gives a very simple geometric understanding of things like the Steinman relations. The sort of 0th order point is that these polytopes geometrize very nicely lots of properties of old-fashioned perturbation theory, which in turn are very useful for understanding some of these things. Okay, another direction is something I certainly mentioned back at the KITP back in 2017, which has always been on my mind in thinking about the whole on-shell program, is that I always thought that there was a kind of a big potential obstacle, or at least a big challenge, which is how, from the on-shell point of view, were we ever going to understand ultraviolet divergences and the renormalization group in the conceptual way that Wilson taught us to understand them, because certainly Wilson's ideas were crucially off-shell. And it was hard to understand how we're going to see things like zooming away from a local space-time point or integrating out off-shell, integrating out shells in momentum space from an on-shell perspective. And what I've hoped all this time, I certainly said this back then, this is not a particularly original thought, is that since Wilson, there has been another way, a nicer way of going back and trying to understand the structure of ultraviolet divergences and even the renormalization group in terms of this Hopf algebra structure on graphs introduced by Kahn and Kreiner. So there's this beautiful coproduct that's defined on any graphs that involves summing over all subgraphs cross this notion of a graph G mod gamma, where you just take all the edges in the subgraph gamma and you shrink them to zero size. So it should be clear why this has something to do with ultraviolet divergences, which has to do with when parts of the graph shrink in position space to zero size. And there are various rules about what you should allow these subgraphs to be. If you want, you can just sum over essentially almost all of them, or you could sum over the ones that correspond to divergent subgraphs. There are different choices, and they all have this nice, but this defines a well-defined coproduct on all of them. So, this is so reminiscent of factorization and other things that we've seen in the amplitudes that I always hope that there would be some way of making contact with our way of thinking about it. And so this is, we started exploring this with some work in progress with my student Aaron Hillman and Sebastian, thinking about both UV and IR divergences in the Wilson line or parameter space, Feynman parameter space language. And let me just sort of summarize what one of the zeroth order fascinating points is. When you think in a parameter space, you immediately in the world line formalism or in Feynman parameter space, starting from a given Feynman diagram, you immediately are construct these semantic U and F polynomials. And now there's a very natural thing to do with these U and F polynomials. You can look at their Newton polytopes. So that means the polytopes that you get by taking the convex hull of the exponent vectors of all the monomials in the U and F polynomials. So if you take literally this graph, this is what the U polynomial looks like. It's a three-dimensional polytope. This is what the F polytope, again, a three-dimensional polytope, looks like. Now, here's the amazing thing, which Francis Brown first told me about last fall, and that we're trying to understand better and characterize these polytopes from various points of view, from various different points of view. The remarkable thing is that these polytopes factorize on their boundaries to other polytopes of exactly the same type. And the factorization is precisely if the boundary of the U polytope is the sum over subgraphs U tensor U, U cross U, while the boundary of the F polytope is sum over subgraphs U tensor F. So there's some detailed differences between them. But the point is that these polytopes precisely capture in their facet structure all the way shrinking subgraphs to a zero size. These polytopes play the same role for unit divergences as the icosahedron does for capturing long distance factorizations. So, and it's also interesting, so it's non-trivial that all of these things are captured by the vertices of the polytope in the same way that it's non-trivial that all the Feynman graphs are captured by vertices of the icosahedron. In fact, a small part of this polytope structure, just that there is a notion of a boundary that squares to zero, captures this Kahn-Kremer-Hopf algebra, and something that we're thinking about is what the rest of the polytope means. But indeed, it is true. It's not just a sort of wild hope that there is a positive geometry associated with the Kahn-Kremer-Hopf algebra structure, and there are these beautiful polytopes that are analogous to icosahedra and their friends for factorization at the level of understanding ultraviolet divergence. All right, I'll just say another few quick things. Also, in the past few years, there have been a couple of positive surprises. For example, we've seen that there's total positivity of SL2R conformal blocks, and that there's some natural interpretation of the conformal bootstrap using cyclic polytopes, and that there's a interesting total positivity in any consistent effective field theory that's compatible with unitarity and even mild forms of locality. That if we take a low energy expansion in any effective field theory for 2-to-2 scattering amplitude, we get some polynomials in S and T. These coefficients APQ, from 15 years ago or so, we knew they have some very simple, just ordinary positivity properties, but much more strongly, these coefficients, this big table of numbers actually has to lie inside a kind of something that's halfway in complexity between polytopes and amplituhedra that we're calling EFdhedra. And one very simple example: if I fix Q and I vary the coefficients in P, if you make these matrices known as Hankel matrices, all these determinants have to be totally positive. So those are interesting relationships between nonlinear relationships between coupling constants of different mass dimensions in the effective field theory. And so there's a natural question: could there be even more constraints needed to fully nail the ultraviolet theory? So this is a huge set of constraints on the low energy effective theory. Can we sort of proceed in this way to learn more about the full theory? So the final sort of new direction along these lines that I'll say something about, which sort of dovetails with that, is thinking about celestial scattering amplitudes, specifically for the purposes of thinking about these questions about ultraviolet completion. And the celestial sphere is the very natural geometry for the flat space hologram. There's all kinds of fascinating work over the past 5 years or so on thinking about various aspects of infrared divergences and soft physics in terms of symmetries on the celestial sphere. One thing that I find especially interesting is that it's natural to scatter boost eigenstates in this framework. So you're not scattering plane wave eigenstates. It's really natural to scatter boost eigenstates. And that means, so that just involves, for example, a 2-to-2 scattering, the following very simple Mellin transform that goes from the ordinary scattering amplitudes, where omega is the center of mass energy and cos theta is the scattering angle that we can translate to this variable z on the celestial sphere. But we just take the Mellin transform of ordinary scattering amplitudes to go to the celestial amplitudes. But while this is a simple transform, it has various striking consequences. One of them is that you can't just take a UV incomplete theory like gravity and Mellin transform the amplitude. You'll get nonsense. So you do not have the luxury of working with UV incomplete theories. You have to work with UV complete theories. I really like that, because if you want to think about something that's going to nail the UV on you, then this is a good place to start. You don't have the luxury to do anything, to do random things. And there are a lot that can be, there's many things to be said about this subject. I'll just mention one of them. This is the work that should have appeared a while ago, except for me, but with Andy and his student Anna Maria Reclario and Monica Pate. One of many interesting things to say about that is that there's a striking difference between the analytic structure of these Mellin amplitudes for field theory and quantum gravity. In both cases, they can only have poles on the real axis, but in field theory, they can have poles at both positive and negative real axis, whereas for exponentially soft amplitudes in the ultraviolet, as we expect when you have black hole production, there are only poles on the negative real axis. And furthermore, the residues on these poles are precisely the coefficients of in the low energy effective field theory expansion. So in momentum space, this is some kind of practical thing. You maybe like to talk about the coefficients, organize the low energy amplitude in this way. But in the celestial sphere, that more invariant meaning is the residues of these poles in negative beta. And it's exactly these guys that, as I just mentioned, have these lots of extra positivity constraints on them coming from the EFdhedra. So this is another place where there's some hidden positivity now showing up in Mellin amplitudes on the celestial sphere. And so this, coupled with the fact that we don't have any luxury to have UV incomplete things, to me, is a fascinating reformulation of the program of trying to completely think about UV completion in a new way. All right, so that's a summary of a few new directions. And do I have about 15 minutes, Jared? Is that right? How long do I have?
Yeah, let's say 15 minutes. Yes.
All right, 15 minutes. All right. So in my last 15 minutes, I just want to take one of these. I want to take one story and tell you a little bit more about it. And most of you, I think, were heard my talk at the Zooplitudes meeting. So I will go through some of the. I'll go through the that more familiar part of the story more quickly and focus on some of the new things that have happened since then. Okay, so I'll be talking about scattering amplitudes and cluster hedra in kinematic space, and this is work in progress with Hadley Frost, Pierre-Guy Plamondon, Giulio Salvatore, and Hugh Thomas. So let's talk again about the bi-adjoint phi-cube theory. Now I'll define it a little more carefully for the people in the audience who haven't seen it before. So we're talking about just a cubic interaction for a scalar field that has two colors. It has to have two colors, otherwise, with one color, this cubic interaction would vanish. Now, as usual, for color theories, we'll do a trace decomposition. And now we have two different kinds of color. So the little a and the big A color. And so we'll have traces with the little a color and big A color. We can have, so I will call them single trace, double trace, triple trace, to always referring to one of the two colors. Now, this theory is the usual double line 1/n genus expansion, where the fact that there are two colors just means that I draw the diagrams, I draw Feynman diagrams on my on Riemann surfaces with genus G. The external T's are just boundary components that I just shove into those Riemann surfaces. And then all I have to do is ensure that the diagrams are consistent with, to be drawn on those surfaces, are consistent with the same orderings for both the little a and the big A colors. Okay, so what we're going to do is focus on the case where the little a and the big A orderings are the same. The other cases, we're just missing some of the diagrams. So we're just going to focus on the case where all the diagrams are there, the orderings are the same. And in this case, the diagrammatics and the combinatorics are then identical to Yang-Mills theory. So for this purpose, you could think of it as really being like just Yang-Mills and gluons. Forget the bi-adjoint theory, except we don't have any polarization vectors upstairs and stuff like that. We're just focusing on the simplest on the pole structure. Okay, so just a quick reminder of what the kinematic space is in these theories. So we can think about the kinematic invariance as just being Mandelstam invariance, or if we draw our favorite polygon in momentum space, we can also think about them as distances squared between 2 points in the polygon, which is the sum of consecutive momenta squared. So we have these xij variables that are equal to xji. And there are as many of these as there are independent Mandelstam invariants. So they're a good basis for all the Mandelstam. And already at tree level, we can start off like drawing these cubic Feynman diagrams, but equivalently, we can draw the dual of those diagrams and the dual or triangulation of the polygon. So we can think about the tree amplitude as the sum over all the triangulations of the polygon, the product of all the triangles in the triangulation of the corresponding 1/xij. So locality and unitarity are reflected in the fact that we are not allowed to have poles that correspond to crossing chords, and that when we do have when we have a chord variable going to 0, we get factorization into the product of the two corresponding polygons. Now, the thing that we're trying to explain is the following surprising fact. So we think we know everything about this dumb theory, just a scalar theory. There's nothing magical or strange about it, but there is something interesting about it, which is the fact that the pattern of poles that can come together is not arbitrary. And what's remarkable is that all the Feynman diagrams, or equivalently all the triangulations of the polygon, actually fit on the vertices of this remarkable polytope known as the icosahedron. This is not an obvious fact. And our usual picture for scattering amplitudes in terms of particles and strings, which makes factorization obvious, does not make this fact obvious. But the fact that the pattern of poles that come together, or the pattern of diagrams, can be associated with the fact that the polytope does know everything. it does know about factorization. Factorization doesn't know about it, but it does know about factorization because all the boundaries of the isosahedron factorize into the product of two lower isosahedrons. So that's a qualitative fact we're trying to understand better. And a more quantitative fact is that there's a hidden symmetry that I've referred to already, that the scattering, if we think about not scattering amplitudes, but scattering forms, that these scattering forms have this hidden projective invariance, which is simply the invariance of the form under a local rescaling of these x variables by some local function alpha x times x. Let me skip that. So the particular story, and there's a simple way of finding a family of subspaces. This was the ABHY family of subspaces that also revealed the corresponding isosahedron, such that when you pull back the form to the subspace, you just get the amplitude. Okay? So we can again ask, where did this ABHY isosahedron come from, which was generalized quickly afterwards to realizing cluster algebra polytopes for all the finite type cluster algebras associated with Deacon diagrams. So we're back to the similar situation as we were with the amplituhedron. There, the kinematic space is just a space of all z's, just these n-ordered z's, and you somehow have to find a question to ask in that space whose answer gives you the scattering form. Now our kinematical space is just a space of all xij. So it seems like a pretty arid and boring space, not much to do. But as I described back in the amplitudes, you just begin by drawing all the points. Okay, so you start with one of the variables, let's say x13, and then you fill out this grid, just translating each point, just translating the I and the j variable by cyclic action. And the fact that we have, there's an interesting fact that the boundaries of the polygon are null or fixed masses. For scalars, it doesn't matter if it's massless or massless, but it's fixed. So we have fixed conditions on these black dots. And so already the kinematic space looks like the inside of this interesting strip. And there's also a notion of causality in this kinematic space-time, because whether two chords cross or not in the polygon is translated in this picture of the kinematic space into whether the chord ij and kl are actually the past and future corners of a causal diamond that fits inside this strip. Okay, and so if we just take this, again, we're just drawing a picture of the kinematic space, but there are different ways of taking chunks out of these kinematic spaces that cover the xij rather than the xji variables once and only once. So there are many ways of doing it, and all of them are equally good, and they give us our picture of our kinematic space. So this is in more detail our picture of a kinematic space is like the inside of this right triangle. Now we have to ask a question in this kinematic space, and the question that we ask is given that you have this hint of dynamics from this causal structure, is we look at solutions of the wave equation with the solutions of the wave equation with a positive source. And that's the beginning of the whole story. So if you just ask in this diamond, you want to look at solutions of the wave equation where the source is positive and you want the solution to remain positive everywhere inside, then as a function of the initial data that you put on this past slice in the kinematic space, you have to carve out some region in this space. And if you sample it at some finite number of points, then just simply asking for it to be positive everywhere inside when the external data is positive precisely tells you that these that the values at the past boundary have to live inside the isosahedron. So that's where the isosahedron comes from. We have a kinematic space. The kinematic space has this interesting, non-obvious to begin with causal structure. And if you ask the question about the wave equation, then with some positivity constraints, this is very much analogous to what we saw in the story of the amplituhedron. Then this ABHY isosahedron comes to life. And once again, we ask that, and there's a conceptual reason for this that I explained back at the Zoomplitudes, that we can just see from the picture that we have something that's manifestly polytopal, but which also factorizes on its boundaries. And finally, the scattering amplitude is a canonical form that's completely fixed by the requirement. It lives on this big space of all the xij's, but it's fixed by the requirement. When I pull it back to a solution of the wave equation, I get the canonical form for the corresponding isosahedron. This makes the projectivity manifest and various other properties of these. Let me not spend time. Of course, it has many, it implies new recursion relations you can use to calculate the amplitudes and so on, but I'm not going to be talking about any of those details here. Let me just move on to talk about how this philosophy extends to loop level. So let's say we just want to talk about the one loop integrand. So once again, I draw my diagrams, my usual Feynman diagrams. But remember, we're talking about the jewels of these diagrams. So the jewel of the box diagram is just the triangulation of now a square with a puncture in the middle. So in general, at one loop, we have triangulations of a polygon with a puncture in the middle. And now the kinematic variables are a little bit more interesting. We no longer have xij equals xji because we can go around the puncture in two different ways. We also have these loop variables that go from a vertex out to the puncture. And we also have this interesting variable that wraps around the puncture that is actually associated with tadpole diagrams. For a variety of reasons, it turns out to be better not to draw this diagram like this, but to draw it as another kind of loop variable with a little x or a so-called tag attached to it. But anyway, when you do that, there's again a kinematic space associated with this problem. Again, a set of the kind of local Gauss's law wave equation of formulas you would write down. And the corresponding polytope has as its vertices, remarkably, all one loop diagrams. Okay? And has all one loop diagrams, including tadpoles and bubbles on external legs and everything. Okay? And in fact, it has a sort of canonical doubling of these one loop diagrams for reasons I don't really have time to explain, although you can sort of mod out by the doubling and just get something which includes all the guys that you want. I also want to comment that there's a stringy canonical form. This guy ends up being the cluster polytope for the DN cluster algebra. If you don't see a DN in this picture, if you look at these two reds, if you look at this bottom slice here, you'll notice something that looks like the Dinkin diagram for D4. That's not a coincidence. So the stringy canonical form for this DN cluster polytope exists. When it was AN, we got ordinary Covey-Nielsen formula and string amplitudes. For DN, we get something else. That it has an alpha prime deformation of this one loop integrand with all the stringy magical properties. And we don't know how this is related to one loop string amplitudes. If it's related to one loop string amplitudes, but we don't know. We don't know if it is. All right. So finally, let me just sketch what happens beyond one loop, and this is mostly what we've been working on. In general, if we want to think about any diagram in this theory, we'd have H traces, and we're supposed to draw these. We have the usual one of Rand expansions. We have to draw H traces. That means we have a Riemann surface with H boundary components in it. It has genus G and L loops. And so those are the Feynman diagrams you want to be summing. But remember, the entire story begins by looking at the jewels of those diagrams. So we want to have triangulations. Instead of a Feynman diagram drawn on a certain Riemann surface, we want to have a triangulation of the surface. And there's a trivial dictionary here, but there's a small interesting thing we've of course already seen, that the triangulation of the surface with H boundaries in genus G, if we had L loops, this has a certain number of punctures now. So we didn't have the punctures before, we have now punctures, where the number of punctures is given by this formula. So here's a simple example. If you look at this vacuum diagram, for example, this non-planar vacuum diagram, you would draw it on a torus. And then, so here's the diagram again where I shrunk the double lines. Now, when I draw the jewel of this diagram, I get a triangulation of a once punctured torus. So I didn't have any punctures up here, but now I have one puncture down here. That's a special case of this formula. Okay. Now, what we've already seen is that triangulations of these surfaces are associated with polytopes that have those triangulations of their vertices, and of course this is intimately connected to surface cluster algebras. So you get a cluster algebra from any triangulation of a surface in the way I've drawn in this picture, and the notion of mutation in cluster algebras is a simpler and familiar one, that the product of two arcs that close is the sum of or the Skein relations, or the sum of the products of the arcs opened up in two different ways. So there's a very natural notion of cluster algebra associated with all surfaces. And so we've already seen at tree level and at one loop that there are polytopes that capture all the quivers, or all the Feynman diagrams, or all the triangulations, all the same thing. There are polytopes that capture all those objects in one and have them as their vertices, and the canonical forms of those polytopes are the corresponding scattering amplitudes. So we'd like to push this to higher loop order, but now something new happens at two loops and beyond. So here's two loop, here's another two loop thing subleading in one over n, so I'm drawing it on a torus. The corresponding cluster algebras are infinite. And so we have to figure out how to deal with that infinity. It's very similar to the infinity we have to deal with in thinking about symbology for n equals 4 superang-mills. And so we want to find some way of dealing with this infinity, and they're seeking these clusterhedra, which are going to do the job. So I'll just say a few things about this, and then and stop. First, let me give you an idea of the challenge. The challenge is that where are these infinitely many variables coming from? It has to do with the fact that I want to think about this variable here, for example, the two loops as corresponding to one of the loop variables. And as far as the loop variable go, as far as the Feynman diagram is concerned, that's all it cares about. But as far as the triangulation of the surface is concerned, I can wind this guy around the other puncture any number of times. So I have this action of the winding, and this is reflecting the infinite action of the mapping class group, which in this case, if I had L loops, would just be the braid group on L strands. Okay. So that's where the infinity is coming from. If I say it another way, there are infinitely many different triangulation. There are infinitely many different triangulations of the surface that give me the same quiver or the same Feynman diagram, and they differ just by the action of the mapping class group on the surface. So that's the problem. What do we want? We want some way to not have this infinity. With the infinity, it doesn't really make any sense. We can't really talk about all the things that we want to talk about in any meaningful sense with these infinitely many variables. So we want some finite object where these are the clusterhedra, where the vertices are unambiguously associated with diagrams of clusters, and where well, that's all I will talk about here, and the fact that there's a projective form, canonical form associated with would be trivial, and other nice properties would follow. Now, what it turns out, and this is, of course, ubiquitous in this entire business, is we're not inventing anything. We can't do anything by our own ingenuity or imagination. Things either exist or they don't. And in this case, it all turns out as we go beyond one loop, the kinematical spacetime becomes richer. As we go beyond the planar limit and or beyond one loop, the kinematical spacetime becomes richer. And we'll find clusterhedra actually naturally living in the kinematical space. And I just want to illustrate with a few pictures and one example, and I'll stop. So let's say we talk about double trace one loop amplitudes. Okay, so the double trace one loop amplitudes, so subleading in 1 over n would correspond to this annulus. They also correspond to a certain class of all loop order cuts. So, but we can think of it as a double trace at one loop. Well, we do the same thing we did before. We follow our nose. We look at what the kinematical variables are. There's variables that connect the out to out boundaries or the in to in boundaries, and then we have these variables that connect the in to out boundaries that have these interesting winding in them. And finally, there's the following very important variable, which is not officially in any triangulation, is not officially a cluster variable, but it plays a crucial part in the story. And in fact, the cousin of this variable is also crucial in getting the square root letters for the n equals 4 superang-mills symbology. So it's sort of amusing that we see it showing up in these two different stories where we need to make the cluster structure finite. The same kind of object is showing up in both of them. But anyway, you'll see how this guy matters in a second. But I'm just going to flash some pictures. What you get just by following your nose. So if we do exactly what we did before in the story of the isosahedron, we just draw the kinematic variables. Then the in-out ones, these ones that have winding, I won't explain it in detail, it was extremely simple, they actually form an infinite cylinder. And the fact that it's infinite, it keeps on going, is precisely the fact that you can keep on winding forever. So one component of the kinematic space has this infinite cylinder. Then there's other components that just involve the in or out variables, and these are just finite. Okay, so they're just sort of finite chunks that look just like the kinematic spacetimes that we saw in our previous examples. And so we have to sort of glue these different regions of the kinematic spacetimes together. And our first challenge is that there's part of it that keeps on going forever. So we have to somehow compactify this part that is going on forever. And it seems, and why can't I just chop it off? Because there are relations between variables. There are mutation relations between the variables, or the linear relations that descend from them, the so-called tropical mutation relations, that want to relate a variable that you before your winding cutoff to a variable after your winding cutoff. That's why we can't just randomly cut it off. But remarkably, if you take any relation involving the guys that go too far, you just replace that relation with a cousin relation involving delta. Okay, and so this delta allows you to canonically stop to canonically just talk about relations between the guys that you are keeping. So that's the first thing that it lets you do. Now, so we know how to stop. Now that we know how to stop, we want to figure out how to glue these in-out to the in-in kinematic spaces. That ends up being very simple. I won't describe that. That's not one of the more interesting parts. The most interesting part is that we have two different regions of this infinite space. One where we're winding a lot in one direction, and one where we're winding a lot in the other direction. And we want to finally glue the entire space-time together. I mean, if we don't, then if we have any sort of variables that don't talk to each other, we have an infinite polytope. So we don't have a sort of finite closed object like we want. So we somehow have to learn how to glue the positive to the negative winding regions. And this is another remarkable fact, is that there are relations precisely between a fixed variable, between the most positively wound and the most negatively wound, these relations which are made possible by the presence of delta. So the existence of these relations is not trivial, and is the way the surface cluster algebra is telling us to use this delta as a compactification of the cluster complex. So there's a sort of a final picture for gluing these various parts of the kinematic space together with delta, like gravity, coupling all the sectors together. Now, I'm going to come back to this analogy in a moment quickly, but delta is like some uncolored thing. It doesn't know anything about ordering. It couples to everyone universally because it's a circle that just goes around that boundary component in our example. And here it is allowing us to couple all these different sectors in the kinematic space together. That's a picture for what the final polytope looks like in one particular example for a very simple case where it's three-dimensional, where it's 821. Okay, so that was the story when you had the annulus, but exactly the same ideas work for the case of two loops, so two punctures, and these are the cases where the corresponding cluster algebras are affine, and there's only a single delta variable. So the mapping class group is just a single U1. And various nice things happen. This delta is a stand-in of the mutation partner for every missing variable. All the vertices of these clusterhedra are unambiguously associated with Feynman diagrams. If I keep some amount of winding and I stop, all the vertices count the Feynman diagrams the same number of times. So I have the same number of I have the diagrams differing by rounding are counted the same number of times, and I have some stuff involving delta. And you also pull back to recover the amplitude as you should on subspaces. So that's the story for these affine clusterhedra. Just have one delta. There's one more example which has a finite number of deltas that's interesting, which is two-loop triple trace. Okay, so these are two-loop triple trace amplitudes that you can think of as diagrams you draw on a sphere with three boundaries. Okay, and here there are three deltas that sort of encircle the three boundaries. And there seems to be a fascinating analogy that these deltas are sort of forced on us in order to make these finite polytopes. We're forced to introduce these deltas. And in fact, what happens is the following. As I just alluded to, if we keep up to some maximum winding W max, we get our polytope, we get our form, we get the amplitude, and then clearly we have to set all of these x's that differ by winding equal to each other. That was the whole point. If we do that, the final amplitude has one component, only minute of diagrams involving the bi-adjoint scalar part without delta. That has a big W sitting in front of it. Then it has pieces that involve psi and delta. So that means that if we keep W finite, at any finite W, we have our bi-adjoint theory, and we have this other sector of stuff, that's delta, that couples to the bi-adjoint with a coupling that looks like 1 over W. And there are various things about this that look gravitational. For instance, again, there are no spin or anything here. I just mean an uncolored particle that couples universally to everything. For example, if I take this APQ example, then if I can look for a pole as delta goes to 0, and if you cut a few other things that are natural in the picture, what you get is the product of the amplitude with the P guys on the outside of the Q guys on the inside, so single trace times 1 over delta. Well, that's a lot like how we see closed string gravitons emerge in open string amplitudes with the innerless diagram. Even more interestingly, if I take this triple delta example, then the analogy with gravity would make you think that there should be some vertex of this polytope, some facet, where these 3 deltas meet. And on that facet, I should have the interpretation as the product of the isosahedra for each one of these different pictures. And indeed, remarkably, this facet exists where the 3 deltas all go to 0 at the same time, and that facet is really interpreted as the product of the 3 isosahedra for the different components. So it's like we're seeing the graviton propagator, quote unquote, and a triple interaction, quote unquote, from this picture. But it remains to be seen what the interpretation is in general. So we're done through 2 loops, some all loop cuts, and I think we're on our way to trying to understand the story for all loops and all orders in 1 over n, where the strategy is to understand these decoupled sort of topological sectors, the generalizations of these regions with different windings, but then include these closed loop deltas that should somehow gravitationally couple all the sectors together. And look, I won't spend any time talking about this. I'm already going on too long. Other than to say that since the Zuplitudes, we've understood a few more examples in some detail. For example, the story of the once punctured torus, as I think is pretty well understood. Here already we have a real novelty that what happens beyond the outline type cases, that the number of these triangulations or the number of these cluster variables explodes exponentially. And that's kind of like a cosmology in this kinematic space. There's a sort of precise sense in which this Markov picture is like a de Sitter version of kinematic space. But the same kind of picture continues to hold. If we only talk about cluster variables, we have some sort of jagged thing which doesn't seem to want to close to form a polytope. But again, not doing anything, just looking at what the deltas are doing that are there for us, we find that the deltas have precisely the properties that we need in order to try and in order to complete the space and make a well-defined polytopes. And starting at 3 loops and above, we really have to deal with the non-abelian nature of the braid group for the mapping class group, and that's something that we're trying to think about. All right, so let me end there. Thanks for your patience. I just want to end with just 2 very big questions that, to my mind, there's been little real progress on since 2017, some, but little. First, what is the jewel of the amplitude? Something that, well, last time at Amplitudes last year, I got myself in trouble saying that only 2 people cared about this, and I was reminded by 3 people they also care about it. So 5 of us care about this problem, but we care a lot about it. I'm sure this object exists. I'm sure it's 2 orders deeper than anything that we've been talking about so far, and is incredibly important to try to get our hands on it and understand. And another sort of persistent mystery is there any geometry, directly combinatoric geometry, anything that lets us think about gravity or really unordered amplitudes directly? And here there's a 0th order challenge right at the beginning. Like, even if you want to talk about a single phi cube theory, what is the amplitude? It's 1 over s plus 1 over t plus 1 over u. It has 3 poles. It should be a 1-dimensional geometry because they just have single poles, but there's no kind of geometry in 1 dimension with 3 boundaries. Related to that, every picture we have for a geometrization of amplitudes involves thinking about singularities as real codimension 1 boundaries. That's what we get in the open string worldsheet, for example, or the isosahedron. is we go to 4 points. It's real codimension 1 to get this bubbling picture. Whereas for closed amplitudes, we see nothing in real codimension 1. We see something in real codimension 2, where we have these long thin tubes between the two spheres. So that's I think to me is a deep mystery. It's the reason why every way of sort of hitting gravity amplitudes has somewhere in it the idea of Yang-Mills squared, because on the colored side, the notion of singularities and boundaries match each other. But we don't know how to make them match without that notion of an ordering. And I don't have anything new to say about this now, other than to say that I'm absolutely positive, as I think many of us are, that while gravity is Yang-Mills squared, gravity is much, much, much more than Yang-Mills squared, and that there's something deep hiding there already at these very, very simple difficulties at 4 points. That maybe there's some correct way of thinking about it that will let us understand a lot more. All right, so and I really hope to see progress on these questions before our next KITP meeting. So I'll end there, and thanks again.
Thanks a lot, Nima. And I will open just for the general discussion on all talks today, because we have just a few minutes left. So Lauren has a question.
Oh, yeah, thanks very much. Right, yeah, so I just had a really basic question. So you were saying that in your cluster hedra, vertices are supposed to be associated with clusters. Right. But now, when you're working with these infinite type cluster algebras, is it more accurate to think of vertices as associated with a subset of all clusters, or is it more like you put an equivalence relation on the set of all clusters?
Yeah, sorry. What I meant is that you can associate them with a cluster, but of course they're not clusters. So what happens in the simplest affine type cases is that what's going on is exactly you're missing some cluster because you truncate. But every vertex you can think of as there wanted to be a cluster variable there that you got rid of, but instead of that cluster variable you have delta. And delta is sort of doing double duty for many different missing cluster variables. Another way of saying it is that those vertices are associated, if you like, with partial triangulations, and then delta. So there was a nice combinatorial rule for who the new vertices are that include delta. But the way you should think about it is that you have all these vertices, and you sort of wind and wind and wind, and you have more and more vertices. They want to sort of keep going to infinity, but you stop somewhere, and then there's a facet with delta, and delta just caps it off. Delta naturally caps it off, and there's a nice description of what that delta facet looks like. And the description involves sort of shrinking the delta loop to 0 size. In fact, sort of thinking about that delta is very familiar from the story of where the tagged arcs come from to begin with. When you think about the punctures being blown up into little annuli with a point on them. So already in that picture, we can understand that we have these different windings of positive and negative winding that turn into the tagged and untagged arcs when you project through delta. We're saying here, you don't have to keep going to infinity. You stop at some finite point, and the deltas are sitting there ready and waiting to give you a finite version of the whole thing.
So is delta sort of saying it's sort of encapsulating the freedom of putting in an arc with some arbitrary number of windings?
Exactly. That's right. Okay. And if you like, the more and more windings you put, the more and more of this polytope is normal, the less and less of it is delta. And that's the sense in which there's kind of a coupling constant, which is the amount of winding. And if you look at the forms you get, and then you just equate all the variables, all the winding variables to each other, you get this big copy of all of them that only involve ordinary clusters, and an order 1 amount that involves delta. And so at the level of the amplitude, what you naturally associate this with is not just the biadjoint theory, but the biadjoint theory plus this other sector of stuff. But you can make the coupling of this other stuff to the biadjoint as tiny as you want by increasing the amount of winding that you keep. But it's really naturally always sitting there. Just like, again, this is part of the analogy, just like in any local theory we like, we can imagine coupling it to gravity as arbitrarily weakly as we like. But it's sort of important that we can couple it to a gravity. So now I gave you simple examples where deltas look like gravity in these simplest cases where we have a finite number of deltas. What happens in general is we have infinitely many deltas, and so we don't yet know how to think about the deltas in the most general case. We have examples where we understand them, like the Markov quiver. There are infinitely many deltas. We understand how these infinitely many deltas compactify the whole story, but we don't yet know how to think about them sort of gravitationally in an obvious way in general yet. But that's part of what we're still trying to understand.
Sebastian? Thank you. Sebastian.
Hi, Nima. I had a question about the UV aspects of the celestial amplitudes that you mentioned. Yep. And I think I asked you this question before, but I forgot the answer, and I wanted to press you on it anyway. So, just so we can distinguish between two different objects. One is the specific integral representation of the Mellin transform that you wrote down.
Yes.
And the other one is the Mellin transform by itself. So then you might ask when the two objects exist, and it might be that for like if your amplitude has some bad behavior in low or high energy, it might be that the integral representation doesn't exist.
No, I mean it doesn't imply. No, it's true, but this is much worse than that. Okay, so and I'll but let me not give you a very I won't give you a very formal answer. Let me just give you the practical answer. Of course, we're used all over the place to the fact that we have, we're used all over the place to the fact that we have integral representations that don't converge and we have to analytically continue somehow, okay? The problem is that, let's do something really simple, like gravity. So the amplitude itself goes like omega squared. So the integral representation is like the integral d omega over omega squared, omega to the beta, omega squared. There are no scales in this problem. There's no interesting answer that you can get for this expression other than something like delta of beta minus 2. So, in other words, or data plus 2, whatever. So, in other words, with these totally scaleless integrals, there's no interesting analytic continuation. All you get are these non-analytic things in beta. Whereas, if you take UV complete theories like string theory, where there is a regime where the answer is analytic, this is the key point. Without UV completion, there is no regime where the answer is analytic in beta that you can then analytically continue away from. Whereas when you start from something like string theory, there is a region where it's analytic, and then you can analytically continue from there. And of course, the fascinating thing is that there is no decoupling, that there is no, let's take alpha prime to 0. That's the whole point, that when you scatter boost-vacuum states, everything is gone. I mean, all energies contribute. Alpha prime just comes out as an overall multiplicative factor in front of the whole thing, and you have to sort of change your intuition. There is no decoupling high versus low energies and so on. So yeah, it is worse than simply the fact that the integral representation only converges somewhere and you have to analytically continue. It's worse than that.
So I agree with that, but I was under the impression that the conditions for the existence of a Mellin transform, at least Mellin transform in one variable, are extremely weak and require something like smoothness or maybe piecewise smoothness in your energy variable. So are you saying that that's not? Yeah. How do you reconcile it with that?
Well, just try to do this integral. You see that there's nothing to do. Integral 0 to infinity, I'll make it to a power. Yeah. What answer can you get? Okay. The only answer that you can get if the power is imaginary is delta. The integral d omega over omega to the I delta is omega to the I b is delta of b. There's not that's really the problem, is that there is no scale, there's no interesting answer you can possibly get from it other than the delta function.
Okay, thanks.
So we have one more question from Atul. Okay.
Thanks. Great talk. Since you mentioned this business about representing Feynman integrals using semantic polynomials, curly U and curly F, I think you wrote, you would know that the answer comes out as a hypergeometric or GKZ hypergeometric function.
Sure, right.
And you basically managed to have this factorization of the graph itself in terms of gamma tensor G mod gamma. Now, if we, you might have come across Lotnikov's paper, a paper on celestial amplitudes, where he shows that tree-level celestial amplitudes n-geometry and squared geometry, which have some propagator poles. When you Mellin transform, you also get a hypergeometric functions. And I have been trying to
extremely ubiquitous in this business. I mean, you know, if I had a much longer talk where I would rhapsodize about this, right? You know, we're seeing these objects all over the place. We're seeing them string amplitudes, stringy canonical form, Feynman parameter amplitudes, the twisted intersection theory. These are all the same kind of objects over and over again. That's not a coincidence. The main part I mean, there are many standard things about these about Feynman parameter integrals. The thing I was trying to say in that very quick section of my presentation is that this bias I had that there is no good way of thinking about the RG or UV divergences purely in terms of Feynman graphs, and you know, Wilson is the best way of thinking about it, and so on. It's just wrong. It's just wrong. The Feynman parameter space picture is the Wilson line picture. It's the world line picture. It's actually very physical, very intuitive, and you can actually see the structure of the divergences beautifully in parameter space. And as I mentioned, Francis Brown first told me that there was this polytope that captures all these guys and it factorizes on the boundaries. And here we're giving a different description of that polytope. I mean, Francis's description involves certain blow-ups of exactly the integral that you're talking about. And you were just saying that these also directly come out of Newton polytopes of the corresponding semantic polynomial. So all I was trying to do is say that this thing that we've seen over and over again at the level of factorization for long distance properties, like ordinary factorization, that there are polytopes that factorize on their boundaries and so on, that there's exactly the same structure, literally exactly the same structure for ultraviolet divergences. And that the corresponding polytopes I can define in one line, they're the Newton polytopes of the semantic polynomial. They do exactly that. And so the fact that those properties, so it's somewhat non-trivial to prove that when you take the semantic polynomial, what defines it is, you know, some things about cutting the graph into trees and so on and so forth. It's not obvious a priori that the boundary structure of that guy is captured by shrinking subgraphs of zero size, which makes you think about ultraviolet divergences. But it is. And the fact that all of those graphs are captured by this polytope, one very small consequence of it is that this Hopf algebra structure exists. But there's much more in the fact that there's a polytope, going beyond the fact that there's that Hopf algebra structure. So you know, we're just starting to explore these things. But I mention it just because 3 years ago, whenever I talked about this, I just raised this sort of vague hope that the structures we're seeing in amplitudes would somehow connect to the Kohn-Kreimer Hopf algebra, if we're somehow going to connect to some nice story for UV divergences on the RG. That was just a very vague speculation before. It's somewhat more than a vague speculation now, because we can see that that there's a polytope and a positive geometry associated with exactly that Hopf algebra structure.
Yeah, so basically that's what I was wondering about. I wanted to study the factorization structure of celestial amplitudes, and I couldn't just factorize the integrand and get a factorization of the Mellin transform. But it seems that the way you are trying to do in this loop level case, by collapsing subgraphs, that might have an analog in tree level Mellin space amplitudes.
It might. I think I would say a little more generally that there's a broad class of integrals of this sort. That the broadest class has the property that, like we see in Feynman parameters, where they diverge somewhere, which is what all these either dim rag or alpha prime in string theory are about. But let's say in loop integrals, or perhaps in the transforms that you're talking about, I don't know in detail, in the most general case, the divergences live in some low codimension region of the whole integration space. So you have to think a little bit more about how to deal with that. The easiest case is where it's already divergent in the top dimensional region, and then all of these polynomials raised to the epsilon powers are regulating it. In all those cases, there's a kind of a well understood way of thinking about this from a variety of point of views, and what you're instructed to do is look at the Newton polytope of the polynomials that are doing the regulation for you, and that controls the structure of the divergences of the answer and other things that you might be interested I think trying to understand precisely what happens in the most general case is still an open and interesting problem.
So at the level of the integral, do you observe the factorization that G factorizes into the A hypergeometric corresponding to gamma times the A hypergeometric corresponding to G mod gamma?
Yeah,
or do you only observe something in the integrand?
Yeah, so in fact, what I told you, this is again that's really a whole talk by itself. I was just sort of flagging an interesting direction, but just to say a little bit about it since you asked, you see what you actually get from a given loop diagram. It depends on the dimension. It depends on all sorts of things. The actual answer. We got the semantic polynomials raised to various powers f and u. So the thing which is totally universal is these Newton polytopes for the corresponding polynomials have the property that I told you. However, what happens is that the actual divergences that you get in the answer, which depend on the number of dimensions you're in, blah, 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 they only sample some of the facets of the polytope. So for instance, this is reflected in the fact that the Kohn-Kreimer, literally the Kohn-Kreimer Hopf algebra, is not just doesn't involve all the subgraphs, but only the subgraphs that are superficially divergent. And already there's a coaction principle, there's a coaction just acting on those diagrams, and everything is consistent. The fact that it's consistent is just a specialization of the fact that it would be consistent for all subgraphs. But in actual integral, the divergences from an actual integral that depend on the dimensions you're in and so on is only sampling some of the facets of this polytope. And this is also something that Francis was telling me as well, is that there's a lot more to this polytope than just controlling the divergences for a given loop integral. But what all the rest of the information means is still not is something to be explored.
Oh, that raises one more question if I can ask.
Go ahead.
So each of these A hypergeometrics correspond to one Newton polytope, one sum over such polytopes. And if you add all these Feynman diagrams, do these polytopes combine into some big?
Yeah, well, that's a big question, and we have it in a few cases. You know, let me give you an analogy. Before we had the picture of the isosahedron in kinematic space, it was obvious that you think of every Feynman diagram as a simplex somehow, but we didn't know how we should add them together because each diagram depends on only a subset of all the kinematic variables. If you think of each one of them as a little triangle, a little simplex, well, they don't all fit together, all very low dimensional, and how are they supposed to fit together into some object that lives in the high dimensional space? And the key idea was to realize that you're looking for a low dimensional form in the high dimensional space, and that they fit together on a subspace. Okay, so with that idea, it makes sense to combine all the diagrams together and they fit into the isosahedron. It would be wonderful to have the analog of that idea in these other cases we have now, where there's a geometry associated with a single graph, but we don't yet know how to add the graphs. And an even earlier example is the story of these cosmological polytopes, where we have a polytope associated with a given graph. That's the analog of a simplex for just a single cubic graph for the phi cube theory, but we don't have the sort of cosmological isosahedron that would put them all together. I should say that given that for amplitude, the story of the isosahedron is sort of closely related to the story of the corresponding world sheet in CHY in a very natural way. Perhaps these recent ideas that Sebastian and friends and David and friends have been exploring on world sheets for scattering equations for ADS correlators could be of some relevance. Maybe that would give us a clue what these cosmological or ADS isosahedra should look like, if any such thing exists. But anyway, there's already the kind of the closest question to what we've answered for amplitudes is already there for those guys. And then, but as you say, there's the cousin of that question for summing over all the graphs in parameter space as well, where I have even less to say about it. But indeed, that would be wonderful if we could figure out what that means in those cases. That's the difference between the story of isosahedra and amplituhedra, which are about full, complete observables, like the amplitudes or at least the integrands for you.
Right. Thank you.
Okay, I don't see any other hands. Okay, no more questions. So let's thank all the speakers of today again, and as well as yesterday. And this is it. So this ends our short mini workshop. And do other organizers have some ending words, or Dave wants to say something?
Just to thank all the speakers and thank KITP once again for hosting the event, I guess.
Yeah, thanks KITP, and hopefully we will be in person back at some point in future.
Yeah.